All right. Let's see if our shooter in
All right,
Las
everybody.
Vegas.
Hello, Belinda. Hello, everyone out there. We're now live on air. We have been delayed. We will be starting at about 1:15.
Testing, can you hear me?
Yes, I can hear you.
Good. I'm going to mute for a while. How's it hanging, guys?
Still, yeah.
Hello, everyone. Neville, can you say hello?
Yes, I can. I can. Hello.
Keep talking.
Hello. Testing. Can you hear me? Can you hear me?
You didn't put the USB.
I can hear you. Can you hear me? I'm talking and I'm talking and I'm talking.
That help.
I'm talking. Can you hear me?
Hello, somebody say something?
Hello. Testing. One, two,
Brilliant.
three.
We can hear you. Fantastic. We're still here just waiting for the group from Alice to arrive.
Okay.
I guess we'll give them 5 more minutes maximum.
Okay.
And then we'll press on because I know that people have got to be places.
All right. I'm going to mute in the meantime.
Okay.
I can't hear anything.
I can't hear anything either, but I'm not sure if we're meant to hear anything.
Can you hear me clearly now?
Yes.
Yes, I can hear you.
Fantastic. All right, we're going to have to make a start. So, welcome to the first Access Habitable Planet online event of 2017. As most of you watching out there will know, my name is Carl Palmer and I am the Access Education and Training Manager. And welcome to this, our very first of this year, one of these events where we try and interact with you guys out there. I know that we have some big groups watching across the country. We have one at the University of Zululand. We have one at UKZN Maritzburg, one in Durban. And we're also supposed to have one big group with us today, and I am supposed to be in Alice right now. But unfortunately, as a result of the strikes in Alice, we've had to, at the last minute, relocate to East London. And unfortunately, right now, as you might be able to see, I am sat in a completely empty room because the Alice group haven't been able to arrive yet. Nonetheless, I'm aware that people have places to be, and so we're going to have to push on and start. And then at some point, hopefully, the Alice group will join us. The idea of these sessions is to try and help you, the students out there, with various aspects of the course that you haven't understood, but also to get a chance to develop some of the aspects and some of the things that you found most interesting. And to help you do that, I've assembled with me an exciting panel of experts. I'm going to get them to each introduce themselves. And in doing so, I'm going to ask them to answer some of the questions that you asked about them. I am going to start in KZN with Sarisha. Sarisha, could you, if you can hear me, please give yourself an introduction? And can you please, in doing so, ask Viwe's Paya's question, what did you have for breakfast? And answer Nombusiso Tichaka's question on what does it take to be a core lecturer?
Hi viewers, I am Sarisha Ramjeawon from the University of KwaZulu-Natal, Pietermaritzburg campus. Please excuse the slight delay that I'm having on the... Anyway, the first question was, what did I have for lunch or breakfast? Well, this is a very intriguing question for me because, I mean, everyone loves food. However, my weight speaks otherwise. I had a long day and early lectures, which means that I actually had to skip breakfast. However, for lunch, I had a Karanija sandwich. So the next question was, what does it take to be a core lecturer? Well, firstly, you have to qualify as a planeteer of access. Then you have to make a video and explain why South Africa is a special place to study Earth system science. Thereafter, a worthy video showing your best communication skills will be accepted. And guys, the competition is tough because you have applicants from all over the world. So know that you are applying with a purpose of teaching others and not just for food. It's free and it's fun. Also have the power to make a connection with who your audience is. No one wants to speak to someone who sounds down and glum. So yeah.
Nice one. Thank you, Sarisha. Excuse me 1 second. Next, I would like to go to Professor Willem. Professor Willem, could you just tell us a little bit about yourself and then also answer Malebo Mukanyani's question of how your week has been?
Good afternoon, Carl. Thank you for allowing me to participate in this nice event. I'm a professor in meteorology at the University of Pretoria. and the department in which I work is called Geography, Geoinformatics, and Meteorology. And my week so far has not been so bad, other than the very nasty experience I had at Home Affairs yesterday, where I had to wait in line for more than 5 hours to collect my new passport. Apart from that, the week's been great. Thanks.
Thank you, Willem. Next, can I ask Belinda if you'd please introduce yourself, and please also ask Dimple Majalati's question of, do you know scrambled pap? Belinda, do we have you?
Hello. Belinda.
Okay, no
I can
Belinda.
see her.
Neville, would you like to go ahead?
I'll go ahead. If you can hear me. I can see her, but you can't hear her. There's something wrong with your microphone, Belinda. Okay, so I'm Neville Sweijd. I'm the Access Manager. I run Access Program, of which Habitable Planet forms a role. I'm not sure if you wanted me to answer any specific questions, but I will tell you that I had muesli and fruit for breakfast, which is unusual. And I've had nothing else to eat because the drawer, which has all the food in it in Carl's office, is empty. So I'm hungry. And my week, I will tell you, has been complex because I've had to impart news on some of our researchers about their funding, some positive and some negative. So that's me.
Okay, thank you, Neville, for that. I think that's everybody for now then, and let's get Belinda. Belinda, can you hear me now?
She can probably hear you, but she can't respond. There's something wrong with her microphone, her sound.
I see, she hasn't spoken to this point. All right, then we don't have a choice but to dive into it, and we'll just have to make do without Belinda for now. The format today is that we're going to go through questions from the student body, and we're going to do it in the order of the course. So the students so far have been through all of the physical lectures of the Habitable Planet, looking at the purely physical reasons why the planet is habitable. And each in turn, we're going to go through those physical sections and answer those questions that the students have sent in. But I'd like to stress that the whole event is supposed to be, we're recording it live because it is supposed to be an interactive event. So we have the YouTube feed up, we have the Twitter feed. We can actually take your questions as they arise as well, in addition to those ones that you've sent in before. So we're going to start with, in the beginning, start of each section, I'm going to ask one of the speakers to just give a quick overview of how that section contributes to making the planet habitable. And in the beginning was originally my talk, so it's incumbent upon me to actually start us off with that. And in the beginning, really is that the whole purpose of the talk is to introduce why we have a planet and no planet at all, and why that planet is made of something that's habitable and not something that's inhabitable. What was the process that we went through to get to this point, habitable planet? And in giving, I'm going to have to talk. And giving my summary, I'm going to have to talk a little bit about the Big Bang, which, as we know from the talk, is the current, most widely held scientific theory on how the universe began. And so in doing my summary, I'm hoping I'm going to answer the questions from Nomtandazo Dlamini, from Masmo Umtulshuli, and Kalipa Zwane, who all asked questions around the Big Bang. Why is the Big Bang the most recognized theory? How did the Earth form in the Big Bang? And is there any other theory to explain the universe's formation? Because the Big Bang is confusing for my grade 8 learners. And I suppose to start by picking up on that last one, the Big Bang theory is the most recognized theory out there because it's currently the only one that explains all of the observable evidence that we have. And that's quite incredible that the Big Bang theory does explain a huge amount about the universe is structured like it is. No other sums for why one and only on the beginning of the universe. And
Carl, I'm sorry to interrupt you, but you're breaking up a little bit. Are you using your phone or your...
Okay.
Maybe you should...
on the phone.
Maybe you should cut your video and see what happens.
I'm going to... Can you... Okay, great.
Can't hear anything now. Seem to have lost you altogether. I can see your video, but I can't hear you. So I think I can see you on your computer, but I can't hear anything. Hello. I can hear all of you, but I can't talk back. I unmuted my microphone, but nothing works. I tried my earphones, but no luck at all. So Carl's got a problem talking. Oh, is that you, Carl? Or was that Belinda? Can't hear anything. Oh, you're back.
Hello.
You're back.
Yes. Trying to turn the video off caused my phone to crash.
Okay, now I can hear you now.
So where was I? Okay, so I was talking about the Big Bang and just reporting that in the talk that I gave, I reviewed some of the key evidence as to why the Big Bang is that one theory that has become the only really tenable scientific theory. And one of the big things is obviously the Doppler effect and the redshift, and the fact that when we look at stars in the sky, all of them appear to be more red than they should be, and that implies that all of them are actually moving away from the Earth and moving away from the center of the universe. And this is key and this is important because if Newton's laws are to be believed, which we hope that they are, then all of the matter in the universe had to start in one place. And I don't have time to go through it now, there's more in the talk, but there is a whole huge amount of evidence that can only be explained through this one theory. Now, of course, science is such that if somebody comes up with a better theory that explains all of the available evidence, then of course, then we might abandon the Big Bang for something else. But it's got to such a point in the maturity of the theory and the amount of evidence that it explains that seems now to be very unlikely. That having been said, I referenced Newton, and obviously Newton's laws were to some extent displaced by Einstein a couple of hundred years later. And so in terms of the schools question, I suppose the answer is really no, because the answer to 2 + 2 is 4, and it doesn't matter how inconvenient that is to teach to the children, the answer will still be 4. We can't just decide that it's 5 because that might be more convenient. Are you hearing me fine, Neville?
Yes.
I imagine you might have something to add.
Well, the only thing that occurred to me now was the concept of a theory. A lot of people get confused about a theory. And a theory doesn't mean that it is just an idea, although actually technically it is. But this pertains to the theories of, for example, evolution. There are many different kinds of theories, and they are different to hypotheses or ideas. The theory is a accepted working idea. And as you've described it for the Big Bang, I think that's good enough.
Sure. And, you know, can you hear me?
Yes.
Okay, perfect. And I mean, obviously, it's important to note that it isn't just an idea. It's one that has been extensively tested again and again.
Right.
Okay, so let's move on to a new brilliant fossil evidence of the Earth that can support the age of the Earth and the solar system. Neville, you had some comment on that.
Yes, it so happens that I'm busy doing a course myself online, which is a course on, also on geography and geology, excuse me, and the history of the Earth. And so I've recently learned about this, and it's the geology really from whence the idea of the age of the Earth comes from. And it should be noted that the thinking around the age of the Earth has changed over the last 200-300 years, whence originally the thoughts were that the Earth was only several thousand years old, to then several million years old, to then a couple of billion, and to the current 4.5 billion. And this is all based on isotopes, on stable and radioactive isotopes, and the ratios of these in various different deposits. And so by looking at the rate at which naturally in the environment there is decay, meaning the use up or the using up of these radioactive isotopes which naturally occur, you can then work out because you have a rate, you know how long they've been decaying for. And on that basis, you can work out the time that it must have taken for the current ratio of the various isotopes to occur. And on that basis, you can then make an estimate of the age of the Earth. And so the current thinking based on these stable isotopes and radioactive isotopes naturally occurring is that the Earth is 4.5 thereabouts billion years old. That's been the oldest rocks that are, or geological formations that exist. However, what processes have happened since then are still up for grabs. So you might have read recently, just last week, in fact, the paper was published in South Africa using DNA, in fact, which also can be compared between different lineages, even ancient DNA, to show, for example, that humans, modern humans, have existed for about 150,000 years. That's been pushed back now to about 300,000 years. So I think the bottom line here is that there are techniques, mostly using physics of atoms and isotopes, which are used to fairly confidently age rocks, which give us the age of the Earth.
Yeah, I mean, I would add to that. I think the physics of the radioactive decay is very, very robust. There's not a lot that can go wrong with it, and the things that could go wrong would generally make it older than it is, right? So we have a minimum age of the Earth.
Right, I'm happy with that.
Okay, that's all I wanted to add.
And note that the Alice students are looking for you.
Oh, I see. I'll pass that on. Did you follow that? The Alice students are lost. They can't find us. If we knew where they were, they wouldn't be lost. The whole concept of being lost is you don't know where you are. Okay, so hopefully they'll be joining us soon. Neville, just very quickly, do you want to go for Yolakazi and Futo's question as to whether you think aliens really exist?
Well, we first have to define what we mean by aliens. And if you think, if we take in the Hollywood definition of aliens being sentient beings that are intelligent and have technology and are going to come to this earth and somehow nefariously take over our world, probably not. But that's not impossible. I suppose it is argued that statistically it is inevitable that intelligent life exists somewhere else in the vast area of the universe. But much more likely, I think, is the fact that alien life, as in non-Earth generated life, does exist somewhere in the universe. That might take the form of microbial life, and it might take the form of some sort of multicellular life forms. It might take the form of organisms with differentiated parts of their body with different functions. All of that might exist. And in fact, evidence for the potential for such non-Earth generated life does exist in the form of what are called exoplanets. So it appears that there might well be planets, Earth-like planets, scattered all around the universe, and there's strong evidence to show that Earth-like planets which may indeed bear life as we know life out there. And so it is highly likely that we do have alien life forms somewhere else in the universe. The big deal is whether or not that alien life is sophisticated enough to seek life beyond their own existence, like we are doing. And even if that were the case... Sorry, go ahead, Carl.
Can I come in there?
Yes.
Reading a review of a paper recently, and there they were presenting, I mean, one of the big paradoxes of astronomy is that we know there are so many planets out there that even if the chances of life developing are tiny, we should still expect loads of it out there. And the paper was arguing that the Earth has actually been around for quite a long time in the life of the universe. The Earth has been around for actually a third of it. And that it might be that there's lots of life out there, but it just takes a long, long time for intelligent life to develop. And that therefore most of the life out there we would expect to actually just be bacteria.
One more thing I wanted to say, and that is that there is also a theory that life on Earth does not emanate from Earth, but in fact was seeded on Earth from life forms that came from elsewhere on the back of an asteroid, in which case we're all aliens.
And that's going to come up later in the course, so I don't want to jump ahead too far.
Okay.
Okay, just very quickly, last in that section, Motisi Motabongi asks, what's the universe made up of? And as a chemist, I'll answer very quickly that two things. It's made up of matter and energy, except that Einstein was the first to show that those two things are actually facets of the same thing. So really, you can just say that the universe is made up of energy. The matter part of that energy is made up of atoms and molecules. They came from the Big Bang and from stars, as is outlined in my talk. Willem?
Yes, here I am.
Did you want to say something?
No, nothing in particular. I just find these things very fascinating. Being an atmospheric scientist myself, I have also some interest in what you've been talking about. And thank you again for the update and the lesson.
Okay, that's great to know. Okay, we're going to move on to Not Too Hot, the second of the lectures in the physical side. And just before we do, can I ask Sarisha if you'll give us just a quick summary of it, please?
Hi, okay, basically Not Too Hot, Not Too Cold talks about our three planets, basically Venus, Earth and Mars. And have this hypothesis in our head that as you move away from the sun, the colder it gets. However, when we use Stefan Boltzmann's law in conjunction with the other law that's explained in light and air, we see that that hypothesis is actually incorrect. The effective temperatures, and we see that Mars is actually colder than it is now, and Earth is minus 18 degrees Celsius, and Venus becomes a negative temperature even though it's closer to the sun. So our hypothesis is tested to be incorrect, and thereafter it's further explained onto light and air.
Okay, nice one. Thank you, Sarisha. That was beautifully short, which was what I asked for, but so short I haven't got the question up yet. I think most of the questions in this section are going to go to you. We just had one question on YouTube, which I will answer very quickly first on the last section, which was Lungi and Ayabelo asked if there's any possibility of life in the sun, to which I will answer no. It's exceptionally hot. So certainly not carbon-based life as we know it. All right, so going on.
Can I answer that? Can I just say something about that question quickly?
Sure, go ahead, Neville.
There are life forms on Earth which are called extremophiles, and amongst those are heliophiles, which are organisms that live in heated areas. And so where you might not expect to find life, you'd be very surprised, I imagine, to find usually microorganisms that are highly adapted. And there is a bacterium, well, I just thought of two, but there's one bacterium that lives in your stomach with a pH of 2. It's called Heliobacter pylori, and it actually causes stomach ulcers. But there's another bacterium that lives in boiling water, in hot streams, and they survive very well there. But I agree with Carl. Boiling water is, but a minute fraction of the temperature of the sun, so it's not really comparable. But anyway, I just wanted to throw that one in.
Okay. You've actually reminded me of something I should have said right at the start, which is that lots of the questions that we got concerned either living things or humans. And those are two things that we haven't dealt with in the course yet. The next section we go on to living things. The final section we go to talk about humans. So I'm actually ignoring those questions for now and trying to focus on purely the physical questions about why Earth is habitable. So if you ask a question on humans or biology, it will come up later. So Sarisha, some questions for your talk. Zizipo Banzi asked, which of the planets has the highest effective temperature?
Okay, from the research that I have done, and also in conjunction with my lecture, only working with Venus, Earth, and Mars, we know that the more negative a number is, the colder it is. So Venus is colder as much as it's closer to the sun. Earth is minus 18 and Mars is even colder. So I would say for the highest effective temperature, we calculated Earth at the minus 18 degrees Celsius. However, I have insufficient data to actually work with the other planets. So I'm sorry about that.
I would imagine that the only other contender for the highest would be Mercury. And I would imagine it would probably win, but I don't know off the top of my head. I'd have to look it up.
We would get back to that.
Yes, but out of the three that we looked at, then yes, clearly it's Earth, which is a real surprise because Venus is a lot closer to the sun, but Venus is just much a lighter color, so it reflects away more of the sun's radiation and therefore should have a lower temperature if it was just a rock without an atmosphere. Okay, Sarisha, and some comments on the possibility of life on Mars. Buhle, Wane, and Sibongile Kubeka both asked that.
Okay, firstly, to date, there is no proof found of the past or present life on Mars. However, there is evidence to show that the surface environment of Mars has liquid water, which may have been habitable for microorganisms. The existence of habitable conditions doesn't necessarily indicate that there's a presence of life. So yeah.
Okay, thank you, Sarisha. And then, Neville, I'm sure you have a comment on that.
About Mars, well, I think she's quite right and covered it, other than the fact that I don't think that there is currently life on Mars. Maybe there's some microbial spores. There certainly appears to have been water on Mars, but
Yes,
I'm not sure whether there is any water there anymore. It might all have evaporated. In which case it's dry environment, too dry. Yeah.
All right, and so then last question in this section, which is, I think, Manzindi, and my apologies for my pronunciation of names. And they ask about Sarisha's model. She calculates the effective temperature of the various planets. And the effective temperature is a model to understand about how those planets function. And they ask, since the model is definitely wrong, isn't there a possibility that it would mislead us, and therefore should it be banned? So should the model be banned, Sarisha?
Firstly, it's a very interesting question. However, let's just make things simpler. Okay, firstly, all models are wrong. Whether it's the illustration of my graphs in the Not Too Hot, Not Too Cold lecture, or looking at the globe of Earth itself, the one that you use at school and you swing around on the axes. So let's use the Earth's globe as the example. The ones that, there's only one planet Earth, and we all know that. But there are many globes of the Earth, right? Firstly, planet Earth is spherical in reality, but the globe is circle and more ball-shaped. Secondly, planet Earth has a diameter of 12.7 kilometers, and is not just a few centimeters as the globes displayed. Thirdly, Earth is not hollow on the inside as the globe. Fourthly, it does not have a plastic surface. Fifthly, if we use a knife, we can cut through the core of the globe of the Earth, but we need more than just a knife to do that to planet Earth. So before I sound more and more ridiculously insane with this example, I just want you to understand that models are representations of what reality you desire to conceptualize. Looking at light and air and the model that Fulufero used to show the diffraction of light. So using my example of the globe of Earth, we can see that it's just a model that totally misleads us, just like my graphs. But why is it that the globe is still being used and not banned? We are still using my illustrations as a model, and I don't think Carl is going to ban those because it's a good example. So yes, that's my answer.
That's superb. Thank you so much. That's a lovely answer, Sarisha. Yes, nobody, I think, is calling for the banning of globes in classroom because a globe is not a Earth, but it is a model that's useful. And exactly, in calculating the effective temperature, Sarisha presented a model. We've used the globes in class. Unless anybody has any last.
Carl, you're breaking up again.
Yeah.
I said I was going to press on unless anyone has any comments on that.
Press on.
That's fine.
Cool. The next section is light and air. I'm going to give a quick summary of light and air. So we move on from Sarisha's talk, where she calculates the effective temperature of the planets and finds out that Earth should be far too cold. Neville, are you hearing me fine?
Yes.
Good. We therefore need to add something else into our model of a habitable planet to try and understand why is it that Earth is habitable. And so in light and air, we change one thing about our model. We've started with a bare ball of rock, the right distance from the sun and a given color. And what we do is we add an atmosphere. And so we find out that Earth has an atmosphere made up of the majority nitrogen and oxygen. and that the atmosphere has some unique properties that make planet Earth habitable. One of them is the ozone layer, which sits in the stratosphere about a few kilometers above our heads. That keeps out radiation and makes the terrestrial environment habitable, so that's very important. But the more important thing is the presence of greenhouse gases in the atmosphere. And this is really the heart of the light and air talk. We hear that our atmosphere contains two very important greenhouse gases, these being carbon dioxide and water vapor. And these greenhouse gases have a really special property. They allow in light from the sun. So radiation reaches us from the sun in the form of visible light. The gases are transparent to this visible light. It reaches the surface of the Earth. The Earth is warmed up. And it's actually the Earth which heats the atmosphere from below. This becomes important in the next lecture because we're going to talk about why the atmosphere is turbulent. But for the purposes of this lecture, when the Earth is heated, thanks to Wien's law, it also radiates, but it radiates much more longer wave radiation. And this is where these greenhouse gases become incredibly important. They are able to absorb that long wave radiation that is emitted by the Earth, and they act like a blanket, keeping the Earth warmer than it should be otherwise. So, in Sarisha's talk, when the Earth was just a bare ball of rock, the right distance from the sun, we end up with an Earth which is far too cold. The greenhouse gases are able to form a sort of blanket around the Earth, trapping this long-wave radiation and keeping it warmer than it should be. Now, in the lectures, we don't present the calculation, but at the very end of Light and Air, we do still come to a contradiction, that in fact, now if we rerun our model, we would come to a planet that is far, far too hot. Okay, so that's a summary of really what Light and Air contributes to the course. I want to say that I have just been joined finally by the group from UFH Alice. I'm hoping if I do this, you can see them.
Hello, everybody.
Oh no, I need this one. There you go.
Well done.
Say hi, everyone.
Hi, guys.
Louder.
Hello, everybody.
Hi, everyone.
Okay, they can't see you very well. Our projector is in the light. I don't know.
Mommy?
I mean, that's rubbish. Sorry, guys. You're going to have to listen. Okay, and now I've lost my cursor. Oh, good grief. All right, so I'm going to move on to the questions on light and air. The first one was asked by Putuma Balentulo and Zipo Yaka. They both asked questions around why is it that temperatures decreasing in the troposphere with increasing height? Neville, you wanted to say something there.
Did I? Oh. Okay, well, the key issue here is that the atmosphere as a chemical entity is made up of matter. And so it has a certain density. And that density then acts like a blanket, and that's what really retains heat in the on the surface of the Earth. And the higher you go, the less dense that blanket is. And so the higher you go, the less heat is contained within that atmospheric part of the blanket. So if you think about a jersey, when you wear a jersey, what's happening is your body heat, which is coming from the surface of your body, is trapped in the air that is kept between the different fibers of your jersey. But the less dense those fibers, then there's more opportunity for the heat to escape. And so effectively, the higher you go, the less dense the atmosphere is, and so the less heat is retained underneath that particular position. So therefore, the higher you go, the cooler it gets. I hope that's an adequate explanation, Carl, if you want to add, or Willem.
No, that's fine.
I suppose you could also conceptualize it that the atmosphere is heated from below. And so the further you go away from the heat source, the colder it's going to be.
Right. Right. That's nice. I mean, that's
both of those play a role. I mean, the less dense also plays a role.
yes.
Because an interesting one is Johannesburg, right? It's colder than it would be at sea level, but it's no further away from the heat source because it's a plateau. So then your explanation has to explain why Johannesburg is colder.
Indeed.
Neville, very quickly, Cleopatra Hove asked, why does UV cause cancer? I'm aware that this is delving into biology, so if you could keep it brief.
Okay, well, I mean, this is to do with the structure of DNA, and of course, DNA is molecular, and it's because it's molecular, it has atoms, and it has to do with the bonds between the DNA molecules. And what happens with UV is it actually changes the chemical structure of the atoms of the DNA. And so you can change the DNA from one form. So you know, DNA is made up of different bases, and you can create a different base by irradiating it. And so it causes two kinds of cancer. One is called the thymine dimer, where actually the thymines bond to each other, and so when the DNA replicates, when the cell is renewed, it makes a mistake. And the other is it affects the chemicals or the enzymes that cause DNA replication. So you get errors in the DNA. And that's what really causes the cells to become aberrant and cancerous.
Nice one. Thank you, Neville, and thank you for keeping that brief. Okay, so next question comes from Onke Jijelo, who asks, do short waves emitted by the sun get absorbed by the atmosphere, or only the long waves that get emitted from the Earth? And so that's a really interesting question. To a first approximation, Onke, you can say that they don't. And the reason that I can say this is because you can actually see the sun, right? If the atmosphere was absorbing the light radiation that was emitted by the sun, then you wouldn't be able to see it. But of course, there are certain circumstances in which you can't see the sun, and one of those is a cloudy day. And so obviously water particles in the atmosphere, when they aggregate together as clouds, do absorb the visible radiation that comes from the sun. Another exception to that rule is the ozone layer, and that absorbs the UV. It's not the visible, it's the even shorter wavelengths, and therefore the ozone is absorbing shortwave radiation. But then, of course, that's very good for us because it means that the surface of the Earth is actually habitable. So that links us on actually quite nicely to the next one I want to do, which is from Naledi Yose, who asks, what causes the ozone hole? Neville, you want to comment there?
Okay, well, I'm afraid I'll have to remember this because I didn't look it up, but I'm quite sure that Willem will be able to help me here. But the ozone concentration is not consistent across the globe. And so it's thinnest, least dense around the poles, and that changes seasonally because it interacts with UV light and with sunlight and the distribution of ozone around the atmosphere. But what has happened is in the industrial age, a number of chemicals, industrial chemicals, have been invented. And those industrial chemicals which have been released into the atmosphere interact with the ozone. And I think they're called carbofluorocarbons, CFCs. They were used primarily, chlorofluorocarbons, used primarily in refrigeration. And that gas is now of significant quantities in the atmosphere to result in the depletion of the ozone concentration, which sits naturally in the stratosphere. And so while the overall concentration of ozone has reduced, when that seasonal variation at the poles occurs, it actually is absent. And so it makes a very low concentration or zero concentration of ozone around the poles seasonally, particularly seasonally. And so we have a ozone hole appearing, as in a gap in the concentration. Of course, as you know, ozone has an important role at that level in the atmosphere, which is to protect us from some UV and other kinds of radiation. And so that's what explains the ozone hole. Please add others.
Well, I can just,
Willem, would you like to reply?
I can just add that there's this well-established circumpolar vortex that occurs during our winter time, and so when we get into spring, this polar vortex breaks up, and so the depletion of ozone is actually part of the natural system or natural process. And so when the big problem called the hole was discovered, in fact, when these measurement devices who measured the concentration found that the concentration was very low, the first data was actually rejected because they thought this cannot be so low because we don't normally see this. And then later on they discovered that the low concentration was actually true. So the breakup actually happens as part of the natural system. What we've seen now is the big problem called the ozone hole is also partly blamed on what we've done to the planet.
Yes, nice one. Thank you, Willem. I'm going to press on to a question from Khalile Zuma, who asks, why is it in the course that light is viewed as a wave rather than a particle? And I think Sarisha has given me an interesting cue for answering this one. And that comes back to, why do you use a flat map rather than a globe when you're navigating in the car? And the point is that the flat map is more useful for navigating in the car. So we have two different models to explain light. We can never see light. I mean, for a start, it's what we use to see with, okay? So, I mean, how can you see the thing that you use to see with? And secondly, it's incredibly, incredibly small. And it's got to a point of smallness where it exists in the quantum universe where the rules that we know don't apply. So we wouldn't imagine that light would be something that would be common to us, that we could understand. It's something that's so, so small that it lives in a world where the rules that we know of cause and effect, the everyday rules, don't apply. And so it's something that the human brain is never really going to be able to conceptualize. But what we do to help us understand it is we build models. Okay, so we make observations of how light behaves. And so somebody saw that light travels in straight lines. And so we think, well, what else travels in straight lines? How can we build a model to describe light? And then obviously, famously, you have Thomas Young's two-slit experiment, where he showed that when you shine light through two slits, it gives an interference pattern just like a wave. And so we said, okay, we can model light as being like a wave. The wave and the particle models are just that. Light isn't a wave. It's not a particle. It's something completely different. Those are just two ways that we can build models that are useful. They make useful predictions about how light is going to behave. Okay? And so in our course, for the things that we were talking about, the wave model makes more useful predictions, and that's why we choose to use the wave model. Just like you choose to use a flat map in the car because it's more useful than using a globe. But you use a globe in the classroom because it shows you where the continents are for education better than a flat map. I hope that makes sense. Does anyone have anything to add?
No.
Good. Last question in the section, I'm going to put to Sarisha, and it comes from Sibusiso Kunene, who says, why is the sun red in the morning?
A lovely question. Firstly, we need to see that, let's compare two colors, red and blue. When we go down the light spectrum, we see that red has a higher, a longer wavelength than blue. And because red wavelengths are the longest, they break through the atmosphere. So the shorter wavelengths, such as blue, are scattered and are broken up. So when we see the red sky at night or in the morning, it means that the sun is setting and sending its light through a high concentration of dust particles. So we can see, looking at red, there's less scattering with an increase in its wavelength and increase in the dust particles. And I think also this is due to Rayleigh scattering, if I'm not mistaken.
Yes, perfect. And Okay, can we move on to the next section?
Yeah.
Can I just add something to that
Sure.
quickly? And that is that why would you say sunsets are redder in Gauteng as opposed to in Cape Town? Anybody?
Would you say that?
Because I mean, well, I don't know if it's absolutely true, but it's been my observation that sunsets are redder in Gauteng.
I would have thought you would go to the Camps Bay to see the most beautiful red sunsets, not Santon.
Well, that's because of the setting of the sun, perhaps. But I'm talking about colours. I've seen much redder sunsets in Gauteng than I have in Cape Town. And I think it's mainly because there's so much more dust in the atmosphere there.
I was bringing up Camps Bay because there's sea salt particles in the atmosphere there, which is the red appearance there. Okay, I'm going to have to press on. We're going to move to the circulating atmosphere and oceans. We don't have Belinda here to give a short summary. Willem, do you want to just very quickly tell us why it's important to have a circulating atmosphere and ocean in a habitable planet?
Well, the circulation is the reason why we have weather systems. And the weather systems are required for us to have rain. And the weather, if the weather systems are configured in a particular way, we can get good rains like we are experiencing over Gauteng at the moment. I can't see the sun setting tonight because it's so clouded over. But we would also like to see that the rain that we get to where the farms are, and then as a result of the nice rain, can grow crops, and we can live on this planet that's habitable. And so it's important for us for the circulation to work all the time. Otherwise, we probably not have any weather.
Okay, thank you, Willem. And just one thing to add from my side is that the circulating atmosphere and oceans also act as a way of distributing heat around the planet. So the weather and the rain that Willem picked up on are just facets of the process of taking heat from the poles and taking heat from the equator and dumping it at the poles. And that process helps keep the planet cool. So in the lectures on light and air, we saw that the planet should be much hotter than it actually is. The circulating atmosphere and ocean is one of the mechanisms that helps explain why the planet is actually at a useful temperature for us to live at. So I'm going to ask a few. We had loads of questions come through on the atmosphere and oceans, and I'm only going to be able to get to a few as we are now short on time. I'm going to start with Arnold Matere's question, which is the equator important factor in the habitability of the planet, or important to the planet? Neville?
Did I volunteer to answer that question?
Yes.
Okay, well, I don't think that the atmosphere is any more important than any other part of the planet.
The equator.
What did I say?
The equator, not the atmosphere.
Oh, I meant to say that the equator is no more important than any other part of the planet. But of course, the equator is the one part of the planet that is least affected by the Earth's tilt, and therefore the temperature and the climate of the equator is generally quite consistent the whole year round, and also quite consistent right around the planet. But it does experience variability for a variety of different reasons. Another important factor is that because the equator is generally the warmest part of the planet, it is from whence most of the moisture, or the area around the equator, is from where most of the moisture that is distributed around the planet is emerging. So in other words, water evaporates from the sea surface around the equator, and then, as Willem was saying earlier, the circulation of the atmosphere then moves that water to different parts of the planet. So from that point of view, the fact that the Earth has a tilt confers upon, and therefore we have different climates at different positions as we move away from the equator. Without that region being the warmest region, then the rest of the planet would not have water. And in fact, the rainfall that falls over Cape Town, for example, the water doesn't come from close by. It comes from far away, and usually comes from tropical regions in South America, for example, where the water evaporates and is brought over by river systems to fall on Cape Town, should it fall, which it hasn't been doing much of lately, as you might know. So the equator then is really important in the context of the whole climate system.
I can tell you it's raining a lot here.
Yes. So I don't think that the further, I mean, the water that falls on the in the more tropical, subtropical regions doesn't necessarily travel that far. And in fact, the water that's falling over Pretoria right now, I know it's raining hard in Pretoria, and I guess down your side too. That's a typical tropical system which is bringing water to the southern part of Africa. But Willem can probably say more about current conditions and whence the water comes.
Okay, go ahead, Willem.
No, it's just interesting to note that water is very old. We're talking about how old the Earth is. And so I just Googled how old is water. And it says here that it could be that the water that we drink and swim in can even be older than what the Earth is currently. So
that's interesting. So Willem, actually, I can come to the next question. Levuhani Matabi asks, where does all the water on Earth come from? So I think you might be getting to that.
Yeah, well, I'm as a modeler, I'm not always worried about where the water comes from, but where the water will be dumped on next.
Neville?
Yeah, so I mean, if the question is what is the origin of water, as in the kind of geological origin of water, that's one question. The other one is from where does the rain come from?
No, I think where does water come from originally?
Okay, so
yeah, how did it get there?
So water is H2O, and hydrogen and oxygen are very common elements in the atmosphere, and oxygen is very reactive, as is hydrogen, and so the formation of H2O is a kind of a foregone conclusion from a chemical point of view. And so as we had the formation of a variety of different elements in the Big Bang, so hydrogen and oxygen were formed, and they quickly formed water. And so there's lots and lots of water in the universe. And for example, meteorites, which we see breaking up in our atmosphere, are probably mostly iced water. So there's lots and lots of water in the universe. It's a very common molecule, and so the Earth has got a very high proportion of water, which is generally on its surface or on the Earth's crust, not in its core. And so that's where water comes from. I think that would be my answer. Where rain comes from is from the ocean.
Sure. I think there was two competing theories on where the oceans and the water originally came from. The one that it did, as you've just pointed out, come from meteorites from out of space, and the other that it actually came from being released from minerals in the crust of the early Earth. And I'm not sure which of those is currently most favored.
Right. So what I'm assuming is that water, so there are many, Carl's pointing out the fact that there are hydrated chemicals which have got H2O as part of their molecular structure, which would release that, and then that water would accumulate as free water. And so when the Earth was being formed and very hot, that would have to have been the case, because otherwise the water would be steam and water vapor, which would have escaped from the Earth or kept or trapped in the atmosphere. So a lot of the water in a warmer Earth might well have been in the gaseous form, and not as in a liquid water, but in gaseous form, and been effectively cloud and water vapor in the atmosphere, which condensed when the Earth cooled.
Sure. Neville, I'm going to have to press on.
Fine.
Once we have water on the planet, we learnt in the oceanography and the circulating oceans lecture about how the oceans and atmosphere interact in El Nino. Tabiso Mabata asks, how does global warming affect a reoccurring natural phenomenon like El Nino? I'd like to put that to Willem because we have him here today, although to note that we haven't actually done global warming yet and that we'll come to that later in the course. Willem, can you give us a little bit of a flavor of that?
Oh, yes, that's a very interesting question. It's very interesting because when we look at our seasonal to interannual variations over Southern Africa, the biggest culprit is what happens in the equatorial Pacific Ocean, where El Nino and La Nina events occur. So it is very important for us to understand how El Nino and La Nina events may play out over the next couple of decades, because this is where most of our seasonal variations are coming from, or is forced by that particular area. So some of the latest research has shown that when we talk specifically about extreme El Nino and extreme La Nina events, and by the way, El Nino is often associated with drought conditions over Southern Africa, and La Nina is often associated with wet conditions over Southern Africa. And that research has shown that the frequency of these extreme El Nino and La Nina years may increase. And so when we have a very strong El Nino, the chances of having drought increases also over Southern Africa. So if we have a projected increased frequency of El Nino events, that means that we will have an increased frequency of droughts. Models that they do this.
That's very interesting.
Yeah, the models that they use this for also say something similar about La Nina events, and that we will have an increased frequency of those too. And part of the reason is because we have seen in the past, in the recent past, that when we have a strong El Nino, that's often followed by a strong La Nina. So what we will find then is consecutive seasons of extreme weather, which is not really what agricultural people would like to know. They would like to get average rainfall every year, but this is not what we will be getting, I think, in the future climate.
Okay, so just to pick up on there, we had another question linked to that, which you've sort of answered a bit. Under climate change, we'd expect both more El Nino and more La Nina events. Is that right?
Yes, that is what the latest research has shown. And this research is, of course, based on evidence from climate models. So first of all, we have to believe that climate models are a good representation of what we know is happening out there, good representation of reality. And if we can believe that it is, in fact, a good representation of reality, we can use these models to see what the future and also the far future might look like. By far future, I mean the next couple of decades. And the modeling evidence suggests strongly then that we will have both an increased frequency in La Nina and El Nino events.
Can I just quickly ask you, Willem, El Nino and La Nina are, as you pointed out, Pacific Ocean phenomena, which have this connection to climate in Southern Africa. But that's one climate mode of other climate modes. There's several other kinds of climate modes. Can you just quickly tell us about other climate modes which are maybe closer to home that also have an influence on our climate?
Yeah, we can start off, for example, by the southern annular mode. And the southern annular mode has strong links with El Nino as well. But I've just read a paper this morning, in fact, where it says that the link between the southern annular mode and ENSO is only when we have very strong ENSO events. As when the events are weak or when we have a neutral phase, this is when the southern annular modes seem to act independently. So there's a climate feature then that oftentimes acts independently of ENSO, and we would like to see that the models that we use to make predictions and projections with do capture these particular seasons when these modes happen to occur independently of ENSO, and in order to see if we can't use this information to make predictions with. We also have the Indian Ocean dipole that's supposedly an important influence, has an important influence over Southern Africa. And then we have some of these interesting dipole structures over this Southern Indian and Southern Atlantic Oceans that are also supposedly responsible for the rainfall and temperature variations that we observe here.
So can I just quickly...
Sorry,
okay, you want to move on?
Yes, please. We're really running out of time.
Okay.
I think Nanga Nonse asked about how ENSO affects rainfall in Southern Africa. I think we've pretty much covered that, right, Willem?
Right. It's mostly El Nino where we see drought conditions, and it's mostly La Nina when we see wet conditions, but that doesn't mean that when there's an El Nino we will have drought. or when there's a La Nina that we will have a favorable season. That's why we also need to make use of forecasts from models to tell us what the models say the most likely outcome might be.
Perfect. Thank you. I'm going to move on from El Nino to something a bit more of blue sky thinking. If we still have you, Sarisha,
Yeah.
can you give us a bit Retabile, Molotsone and Rupu Yapi both basically asked, can we give an explanation as to why the ocean is blue?
Okay, I love this question because I've discussed it. I mean, there was a discussion at HPW 20 when I attended. So basically, we need to understand that just like how we have the wavelengths which decrease for blue color, we see the majority of the radiation incident upon water is not reflected. It's either absorbed or transmitted. So longer wavelengths and the near-infrared radiation is absorbed more by water than by visible wavelengths. Therefore, water appears to be blue or blue-green due to the stronger reflectance at the shorter wavelengths and darker if it's viewed at the red or near-infrared wavelengths. So the factors that affect the reflectance of water is the depth of the water itself and the materials within it, and also the surface roughness. So more logically, if I have to go to the Cape Point, and if I have to look at the Indian Ocean and the Atlantic Ocean, we can see that's where the two oceans meet, but they have two distinct different colors. This is all due the sea floor itself. It's not basically the water, because if I have to scoop some water off the Indian Ocean into my palm, it's going to be clear. And if I have to do the exact same thing in the Atlantic Ocean, it's also going to be clear. So it's not the water itself that has the color, it's more of the reflectance. So also there was a part where you, why does the ocean water differ from lakes and dams? This is because lakes and dams are, they basically water bodies that do not have the constant movement of water as compared to the ocean. So we can see that they probably have more pollutants and nutrient buildup and algae bloom as compared to the ocean itself. I hope that answers the question.
Perfect. That was lovely. Thank you, Sarisha. I'm well aware.
Carl, do you have time for me to add anything to that?
Okay, if you'd like to, very quickly, Neville.
Very quickly, let me just say that ocean color is a concept used by remote sensing people to look at productivity in the ocean. So there are different wavelengths at which you can look at ocean color from a satellite, and often that is a measure of how productive. So oceans can look quite green at the surface in certain times of the year because of algal blooms, and even red, depending on what types of algae. But I just wanted to say that you can measure the ocean's color and use that as an index of productivity.
Perfect. Thank you, Neville. Okay, so I'm aware that we've run out of time, but that we started 15 minutes late. So I'm going to try and wrap up the last two sections, which are both small, within the next 15 minutes, if we can. We're going to start with modeling. Willem, can you just give us a couple of minutes? Why is modeling important in understanding a habitable planet?
Well, modeling is important because without modeling, I won't have a job. The modeling is very important for us to know what the future might hold for us, because if we want to be forearmed, we need to be forewarned, and models are the best tools to do this. For example, the rain that we've mentioned before with Gauteng, it was nice to know that we can predict this, because some of the rain and the weather systems associated with what we are observing at the moment is also associated with extreme flooding, for example, or extreme winds. And so it's good to warn the public of what might be happening over the next day or so. It's also important for us to model what the season might be like, because the farmers are interested to know whether or not they should worry about a drought or a continuation of drought, or and maybe perhaps another favorable season like the one they've just had. It's also important for us to model what might happen over the next couple of decades, because we need to plan ahead. Maybe we need to build more dams. Maybe we need to build deeper dams because we're going to have more heat. So we don't want to have evaporation becoming a problem for dams that we have. So modeling is extremely important for us to make sure that we have not only a habitable planet, but a sustainable planet.
Perfect. Thank you, Willem. Getting into the students' questions on modeling, Lishle Kumalo asks, is a train set a mathematical model? The answer to that question is no, it's a physical model. For a mathematical model, we would have to be solving some sort of equation. I think Avella Pamela asked, why is it important to learn modeling? I think you've covered that in your summary, really. Willem, do you have anything to add?
Yeah, I think there's also different aspects of modeling. We know that at the CSIR, for example, they are building an Earth system model. So people who are involved with that particular enterprise needs to know something about the different equations and the different schemes that they need to apply to the equations of the atmosphere in order to build a model. Then we have people who are users of models. For example, people who work in the weather forecast office, who make a forecast whether or not this plane can land over the next couple of hours at OR Tambo. They need to understand what the model can do for them. So they have to be model users and trained as such.
Can I ask a question, please? Willem, I hear people model this, model that, and there are people making all sorts of assumptions and they're like making estimates and they're building these mathematical models. Why not just go and measure and make assessments based on measurements? What do models do that measurements don't do?
Okay, we used that approach long ago when we started to develop statistical models that can tell us something about what the future may hold by looking at antecedent conditions. And there's strong evidence that building physical models that's supposed to be describing this whole complex Earth system in which we operate, they are needed in order to make predictions that are more useful than what we may get from just using information of what happened in the recent past or even statistical models.
So is it because the system, okay, I'll leave it there. But I just want to say that systems are so complex that we have to have models and then we can start to change things in the models and then we can see what would happen and then we can test it in the real world.
Okay, thank you very much, Neville. I want to move on just the last question on modeling to answer these ones on Nokolo Lukashe asked, what does it mean to say a model is wrong? And then Princess Angben Yaga says, all models are wrong, but some are useful. What does that mean? I'm going to go to Sarisha first, and then maybe hear from Willem for just a quick bit. It's really examining that phrase, all models are wrong, some are useful. Sarisha?
Okay, that just takes us back to the first question that I've answered, where I gave you the example of planet Earth and using the globes of Earth at school. And we see that models are only used to make our lives simpler and conceptualize what we are trying to portray. However, we cannot work with the actual reality itself. Like, if we want to calculate distance, we're not going to use hundreds of rulers. We're going to use a scale. And these types of examples or models as such make our lives simpler. And we can't be working with huge models. So the globe of the Earth that's used at school, although it misleads us, it cannot be banned. So I think that to answer that, I'm not going to be repeating myself. So to answer that question fully, we can just go back to the beginning of the live streaming.
Sure. Willem, do you have a comment? And maybe you can also address Zesipo Vakalisa's question as to can there be a correct model?
Well, we can only use models to give us some outlook on what the most likely situation might be in the future, whether it's the next couple of hours, days, months, seasons, years, decades. So we need to realize that we cannot actually make use of a model to make so-called deterministic statements. We cannot say tomorrow at 3 p.m. the temperature in Franschhoek will be 27.3 degrees Celsius. If we want to do that, we will find that models are always wrong because no model can actually predict with such accuracy even what the weather might be in a couple of hours from now. So what we need to do is to use these models to understand something about the uncertainties associated with statements. So we can say, for example, again, using the example of Ronzoek, the temperatures tomorrow at 3 p.m. is very likely to be somewhere between 26.9 degrees Celsius and 27.9 degrees Celsius. So the models that we use then give us information about what the possible ranges are in terms of also the likelihood of it occurring. And when you start using models in such a way, I think this is then when you start to find most benefit in you.
I could put it to you, Willem, that you could create a correct model. You could build an exact reconstruction of the Earth, atom by atom, in exactly the state of the Earth now. And by tomorrow afternoon, your model Earth would give you a correct prediction of what the weather is like tomorrow afternoon. But that would be completely useless.
Why would it be useless?
Because you'd already have experienced tomorrow afternoon. It will only give you a prediction as it actually happens at the same time. No, it has just gone through a huge
Can't you
amount
run it a few hours ahead?
You could, but how would you know where to start the starting conditions?
Right, okay.
To get the starting conditions, you'd have to start from where we are on Earth now.
So I also want to say just that models have built-in biases because they're not perfect representations, but it's from those errors that you can learn. And you can do sensitivity tests to see how sensitive various representations of real life are to various drivers.
Just like example with Not Too Hot or the Globe, it's in knowing what's wrong with it that you learn something.
Yes.
Okay, I'm going to close modeling there and just quickly in the last 5 minutes go through the miscellaneous questions. Buhle, are you with us? Did you see she appeared? I think she's gone. So I'll leave Bushle's one. Nombuso Mhlongo asks, is there a cutoff time we need to submit our exams on Sunday? So I'll answer that very quickly. No, there's not. As long as they're there for the elves to mark first thing Monday morning, they'll get marked. Do we get certificates for finishing? Velesile Mkanzi asks. The answer is yes. Moving on, I will go to, why do scientists shy away from engaging in political and social issues? That's Pusaleto Takielame. Neville, you wanted to say something there.
Did I? No. Well, let me say that they don't. That's not true that they shy away. I certainly, scientists, as I like to say, scientists are people too. And it's important that scientists have a point of view. However, when it comes to dealing in science, it is dangerous to purport a particular scientific viewpoint as the be-all and end-all of interpretation. I want to use an example from fisheries. I used to work with fishery scientists, and they would make an assessment of the stocks, and they would make a recommendation on how much fish should be caught. And they would make that recommendation to the minister, who would invariably take that information and make a decision based on that information, but not necessarily adhere to the scientist's point of view. And they would freak out and say, but it's scientific. How can you argue with the science? And the reality is that the minister also has to take into account that there are fish factories which employ people, and that there's food security, and that there's a whole lot of other factors to take into account. So science can't stand independently as truth. First of all, because there's uncertainty in the science, but secondly, because science isn't the only consideration. And so scientists, as scientists, need to be careful, excuse me, how they use their results, but that doesn't preclude them from having a point of view by any means.
Sure. And that comes back to our story of the professor of the equator, in fact, that illustrates those points nicely. I notice we have Buhle here. Buhle, do you want to say hello? And I just answered your question with them.
Go on.
Yourself.
Hi, Carl.
Hi,
and hi to everyone else. I'm sorry, I'm at work and I'm using my business hours right now, so don't mind my background at the moment. And I also need to go and catch my earphones so that I can hear everything.
No worries. We'll catch you next time, Buhle. Thanks. Sorry about that. Okay, why is planet Earth so complicated? Came from Modesty, Sitole, and September Langer. I mean, that's a great question, and I wish I knew. Einstein, I think it was, who famously said, if he had been with God at the moment of creation, he would have suggested something a little more simple. How does the professor trick work? Oh, sorry, that was Modesty. Excuse me 1 minute.
Can you all put your microphone on mute if you're not talking, please?
I've done it. Okay, sorry, it was Modesty's question was actually how does the professor do his trick at the equator? And the answer to that is, I mean, how does any magician do any trick? It's sleight of hand. It's a magic trick. He's taught himself to do it because he knows he'll get paid for it. We then had a whole bunch of questions about the involvement of Babes Wadumo in the course. That came from Sibonello, Pelindia, Sizwe, Washu, and Pilo. So I want to put that to bed for now by saying I will be taking no more Babes Wadumo questions, except for one at the end. Saki Titi asks, why don't scientists believe in God? Willem, you wanted to say something on that?
Well, I first of all have to say that lots of scientists do believe in God. I'm a scientist and I do believe in God. This was a big problem for me when I was growing up because I developed early on in my life, by the age of 16, a big interest in meteorology. And I started to read more about the scientific process. And then also at the same time, I was being brought up in a very religious house. So how do I reconcile science and religion? It was a big challenge for me because the Bible says, well, Christians, I have to believe in the Bible, the earth was created in 7 days. So how do I match that with what I see in the scientific literature? Well, that is a big challenge for me, but now I have come to the point where I can live as a religious person and as a scientist. So I don't think it's true that scientists are atheists. I know a number of scientists in South Africa that are anything but atheists. For myself, I know that the question always comes up, so how can you say that you're a scientist and what about evolution? Well, for me it's easy. I believe God creates through evolution. It's just one of the processes that he uses to create life. So for me that's an easy question. But just to get back to the original question, I don't think you're a scientist that you have to be an atheist. I certainly am not one.
Yeah, I mean, there's certainly plenty of scientists who believe in God. And in fact, the Pope believes in evolution. So it goes back the other way as well. I will move on. Are high schools and primary schools involved in HPW? If not, why not? Natembe and Ponchani. Sarisha, you wanted to say something there?
The answer is yes, they are involved. And this is another opportunity for the Planeteers. As soon as you are done with your course, you are allowed to host your own mini HPW at any school after drawing up a whole program. So yeah, I don't know if you want to add anything there, Carl.
Yeah, perfect. Yes, we're having an open call at the minute for anyone who wants to run a schools program. Ruru Yapi asks, for Carl, what does it take in your position? What is your drive and motivation to do what you do daily? That's an excellent question. I've actually been on a trip. I'm in the Eastern Cape now, as I've said, with this group here, and I've just come from Walter Sisulu University, and it's been a difficult trip. It's been pouring with rain. We've had rooms flooded. We've had campus strikes, and so it would, on the face of it, and also we've had the internet problems today, look like it's a very depressing job. But actually, I would say that working with all the students, we've got the group here behind me, the students at Walter Zulu I met yesterday. I meet such interesting people, and I hear such great stories about what people learn and how the workshop helps them, that makes it an absolutely fantastic job and absolutely worth putting all of that effort in. Lastly, I can't see who asked it.
Can I add something to that, please? Can you hear me?
Yep, go ahead.
Yes. It's just that today we heard that Willem Landman student, Patience Shivambu, who is no longer Shivambu because she got married, got her master's degree. Well done, Willem, and well done, Patience.
Thank you.
And it's really, science in and of itself is fascinating and exciting as a career choice. It's a wonderful opportunity, really a special lifestyle. But it's also, as Carl, I think, has alluded to, the opportunity to give other people that opportunity and to provide for development of individuals. That is very motivating. And I think we all enjoy that. And I think Carl in particular enjoys that most of all. So I just wanted to throw that one in.
No, absolutely. And I do really enjoy coming to places like UFH and Walter Zulu. For all of the fun that we've had, I meet some of the most amazing students, and it's always worthwhile me coming to these institutions, and I'm always made to feel welcome. And I hear just such good stories about what HPW and Access has been doing to help develop young people. And also, you know, with people like Sarisha, who we've had talking a lot today, Buhle there, how the students come back and actually help each other and actually teach each other is a wonderful experience to have. And so I'm always motivated to try and facilitate that. I'm going to finish one very last question, which was from Buntu Tuana. And Buntu asks, can you twerk like Babes Wadumo? My answer to that is I'm going to demonstrate immediately after the broadcast. So hang on and you'll see me doing that. Before that, I would like to thank everybody on the panel. Thank you, Willem. Thank you, Neville. Thank you, Buhle, for just popping in. Thank you, Sarisha. I apologize for our late running and for our technical issues. We did have this big problem with the Alice strike, and that set us back.
Let me just say,
next time, hopefully, we will deliver something a little bit more smooth and be able to get to some of more of those questions online.
Just to say that thank you to the Alice people for sticking there and sticking with it, and I hope it's been worth a while to make the trip. We're always faced with challenges when we do these events, but we must keep doing them because they can only improve. So thanks all very much. And well done, Carl.
Thanks, everybody. We'll bring it to a close there. You just have to stay on if you want to see Babes Wadumo style twerking. Thanks, everyone.
Thank you, Carl.
Cheers, everybody.
Cheers.
Bye.